So we finished up our last unit on those complex applications of trig and machining and mechanical applications. We're going to spend the next couple of weeks talking about compound angles. Compound angles will occur in a few different settings. There's drilling. So for drilling, if you're looking at a piece from the top, so the entry spot, let's locate it right there. But the exit spot is not only off to the side, but it's also up and down, so like this. So you not only have to angle that way, you have to angle off to the side as well. So when you do that part, what's going to happen is if you're looking at the drill press from the top, if this is the table of the drill press, and the drill, of course, is hovering out here somewhere, you're going to have to take that piece and twist it so that the entrance and the exit are lined up perfectly side by side on the table of that drill press. That's your first angle. That is called an angle of rotation. You have to rotate the part so that those two holes are lined up side by side or perpendicular to the axis of the drill press. Now, of course, those holes are still not directly above each other. So if you're looking at your drill press from the front, the second thing you have to do is you're going to have to tilt that table so that now that entry hole, the exit hole are straight up and down from each other. That angle there is your second angle. That's going to be called a tilt. We're going to be dealing with rotation and tilt. So this rotation up here, there's that angle would be like that angle there. Similar to drilling, you have an angular milling case. Compound angular milling would be when we have a block material and we're going to cut the corner off of it like this. Like that. So again, we're going to be looking at our mill. We're going to have to rotate that. Looking at the table of our mill, that has to be rotated so that this part of the corner, that top edge, that would be this edge here, is now perpendicular to the mill, or parallel to the mill, whichever way you want to look at it. That's your rotation there. And then the table of the mill has to be tilted. So that surface that's going to be milled off there, this surface here, is now going to be level. The operational plane of the mill. Then we have intersecting surfaces. Intersecting surfaces occur when we have two angular surfaces come together. So right here, this is a block. You look at it from the front side. can cut off like that. If you look at it from the end, cut off there. So what we're looking at is this surface here, lining that surface up so that if we want to run a tool, a deburring tool down it, just take the edge off of that surface, give it a little bit of a round over, not sharp or whatever. And we can line that up. So again, you can see there's going to be a rotation there. Rotation will be turning that part. That corner again is parallel or perpendicular, however you want to look at it. Tilt it. Once again, so that edge is level to the plane of the machine, level to the floor, if you want to call it that. Now, dealing with these situations, the math is really not that tough. The tough part is visualizing where the triangles are, because this is going to be really the first work we've done in 3 dimensions. And so some of our triangles are laying flat, some of them are standing up, some of them are on the angular surface. So the hard part is figuring out where exactly is that triangle. I do have some 3D models here, chunks of wood that I can hold up and show you to help out a little bit. Because I'm drawing it on paper, it is kind of hard to show where those triangles are when they're standing up or whatever. What we're going to look at today is we're just going to start looking at a simple box. Like this. I'm going to give it some dimensions. Like that. And what we're going to try to describe here, define the path, goes from this upper top corner to this lower bottom corner. Give you guys a minute to finish up drawing there, because I realize it's not horribly simple to draw out. As you can imagine, this next couple weeks is a stretch to my artistic talents as well. So the first thing we need to define, well, one of the things we can define here is the length of that path. The length, if we look at it, can be found a couple of ways. First, what I'm going to do is I'm going to look at this bottom. I'll form that triangle there in green. The right triangle. Redraw it over here. There's my right angle. This side's the 1.8 inches from here. And this side's the 1.2 inches from here. How would I find the length of this opposite side, this hypotenuse here? Got it. A squared plus b squared is squared. We'll do the shortcut. Square root of 1.8 squared plus 0.163 we get. That hypotenuse. Now, if we put that in there, now I have this triangle here. Now, this would be a right angle. This is the 2.163. This is the 0.8 pi. How am I going to find the hypotenuse of that? Same thing, right? Square root of the 2.163 squared plus the 0.8 squared. .307 basically. Round it off. Now here's the thing. That 2.163 in there that we squared, that was really square root of 1.8 squared plus 1.8. Squared that and did the 0.8. Well, what happens with this squared and square root here? Cancel out. So this is really the 1.8 squared plus 1.2 plus 0.8 squared. We don't have to do them separate and then put it into the next one. This is called the three-dimensional Pythagorean theorem. Whenever we have a box, so that we have three sides that are all perpendicular to each other, find that corner to corner distance, we can always just do that. Let's say I have a box like this, 0.3 inches, 0.7 inches. Find the distance from that corner to that corner. That length will come out to be the square root of 1.3 squared plus, somebody fill in the blanks.
0.7 squared plus 2.
Perfect. 1.3 squared plus 0.7 squared plus 2.1 squared. I just take the three dimensions, I square each of them, add them together, and then square root. What's that give us for the length? 0.567 inches. Perfect. So we can find the length. Now, if we were drilling, that would be the length of bore. If you're looking at your cut time calculations that we did back in Unit 2, that would be an important piece of information. You got your length of bore, you know your feed rate. You find how long it's going to take to drill that for that hole. While we're at it, let's take a look. If I draw this line across there, take another look at that green triangle there. Now this dimension here is 0.7. Down here is 1.3. I'm looking at rotating this on a table. What I'm doing is this would be the one that would be parallel side to side. And I'm turning it so that this one is parallel side to side. So the amount of rotation is just this angle right here. Now from that angle, if that's the angle I'm looking for, the 0.7 is which side? Opposite. The 1.3 is adjacent. What trig function uses opposite and adjacent? Tangent. Tangent of an angle is opposite and adjacent. Well, here we are looking for the angle. You know, the opposite side is 0.7, the adjacent side is 1.3. How do we find that angle? First tangent, very good. Tangent of 0.7 divided by 1.3. 8.3? That is R, the angle of rotation. For this drawing here, I want you to find that angle of rotation for me. How do we find R? What trig function?
Tangent.
Tangent. So we're going to use inverse tangent of what?
1 over
1/1.6. That gives us that R equals 22 exactly. Well, actually, go 32.01. When we're rounding, we want to take our angles to 2 decimal places, basically. unless it specifies more. 2 decimal places will get us to within a little bit under a minute, which is really precise. I mean, like I said, 15 minutes is really the most precise I've seen anybody in this area. That should be good enough. For our lengths, we want to go 3 to 4 decimal places because those are down to 1,000. Now, the next thing we want to find, draw my drawing a little differently here. I'm going to use the same dimensions. I'm just going to redraw it just a little bit differently so I can see it better. Six, 0. I just rotated my drawing a little bit. So we just found here, this is 32 degrees. I now want to find, if this is my path still from here to here, there are 2 angles I could find. In this first homework, we're going to find this angle. I'm just going to label that angle A. It's really what it is an angle of elevation. Once we have angle A, we can find this angle up here easy enough. That is actually T. That is the angle of tilt. We're going from this being straight up and down, this being straight up and down. So T is the actual angle of tilt. Look at this triangle here, and I'm going to label angle A. We're going to find A first here. Only thing I know right now about that triangle, this is 1.20. However, you all can very quickly find this side of the triangle by doing what?
All 3 dimensions.
Yep. There you go. That is our length of our whole path, our length of bore if you want to. So yes, it's the 3 dimensions. Squares. 1.6 squared, 0, 0 squared plus. There's 2.236. Now that we have that, how are we going to find dimension A? Fine, good. The 1.2 is opposite. 2.236 is the hypotenuse. Sine of an angle, the opposite over hypotenuse. Here we know the opposite side is 1.2 and the hypotenuse is 2.236. How do I solve for A? That's 32.46. Angle of tilt B up here. 7.54. Just the complement of that, because we have the right angle here, that takes 90 degrees out of our 180 degree total. The other 2 angles have to be complemented. path here. Find angle R. I want you to find angle T up here. And I want you to find the length of the bore. A couple minutes and we'll go over that. Find R if we look at that triangle on bottom. This is 1.2, 2.1. R is going to be found by doing tangent of the 1.2 over the 2. That give us for R. (9.74 degrees). We're going to have to come back to T. The length here is going to be found by doing the square root of 2.1 squared plus 1.2 squared, 2.8 squared. What does that give us? 3.7 exactly? 0, 0. Oh, couldn't have planned that out better if I tried. And then T will be the inverse sine. Will be the 2.8 here, 0.70. How do I find T? Actually, T is not going to be inverse sine, it'll be inverse cosine, because T is up here, right? A would have been inverse sine. So inverse cosine of what? Goes on top. Okay, good. Over 0.7, giving us an angle of 3. Those are the 3 vital pieces of information we would need to properly set that up if we were drilling or other possibilities. I gave you guys the packet last week for this, right? So, out of that packet, we are looking at the first section of homework. Starting on page 392, actually it's just page 392. 1 through 6. Finding the angles